to everyone. So we'll welcome on behalf of the organizers. Let us start with a welcome note for the day 3. Okay. Today we'll be discussing about some basics of this. Yesterday we have covered some functions which are necessary, which will help us to create some sort of a descriptive statistics, right? Summary statistics, that and all. Now, today and in the afternoon session, we covered some basic 2D graphs like a univariate analysis. Am I audible?
Yes, sir. Yes, sir.
Yeah, someone is raising hand. I don't know. There is some. Okay. Yesterday's afternoon, we have covered some basic graphs. Now we'll go a little advanced by covering 3D data visualization, that how to have a 3D scatter plot, how to create overlaying density plots, okay, how to have the box plots and different variations of the 3D. And moreover, I will try to make you aware that what other packages are available for this in R, particularly for this what we say, this graphical thing. To have a plots in graphs, I mean, to have a graphical visualization in R, we have many packages available. A few I will list. Okay. 1 minute. I am just opening the file now. Yeah. So let me start my session with sharing the screen. First, I will show you a document where I have the packages which are supportive enough to present the data with proper aesthetics and appealing way. And later we will come to see the discussion part of today's topics. Okay, fine. Let me share the screen. Yeah. Fine. Hope you are now viewing my screen. Okay. So today what we are trying to understand is what are all graphics, I mean, packages that are available for extensive data visualization. Okay. So what sort of colorings we can do, what sort of rotations we can see, how a 3D scatter plot can be viewed, how density plots of a particular categorical outcome variable can be viewed, how to make use of each and every variable in the data to the maximum extent to give out some better understanding of the data what it has. Okay, now here are the some graphical packages. ggplot2. GG is nothing but grammar of graphics. Okay, lattice is another beautiful package. RGL, rotated graphic libraries. Today we are using this RGL. Plotly is amusing. Plotly is very interesting package where you have a proper graphical view. VFX effect will be there. Grammar, graphic gallery, easy Gplot, Scatterplot 3D, Plot 3D, RCMDR, EZR, CarPlot, GG CarPlot, Performance Analytics, R Color Brewer. R Color Brewer is nothing but a kind of a cheat sheet and other sum of functions which will help you to choose the color required to depict the scenario of the data. Now, along with thing, you have EZR. These two packages are like menu-driven packages. Okay, even in this R, most of the people who love programming, they go with other packages. But when coming to this RCMDR and EZR, these two packages are a kind of a menu-driven. Once you load this package, install.packages RCMDR dependence is equal to true. Okay, once you load the package, once we call the package using a function called library. So, but whenever you want to use a particular package, the way to call the package is library RCMDR, library CarPlot, library RGL. Okay, now coming to the RCMDR and EZR, These two are menu driven, like how you do with Excel, how you do with SPSS, how you might have done with these two packages. In a similar way, you can choose a menu driven kind of option. But I personally suggest every one of you that to go not to entertain too much of this menu driven kind of a thing. Once you start scribbling the code, then you will understand, okay, I want to get the main title, so I have to use main argument. I have to give the x-axis, I have to use xlab argument. I have to color the panels, so I have to use color function argument. Like this, step by step, phase by phase, layer by layer, you will be able to understand when you start with coding of R. Okay, so like this GG plot is there, plot 3D is there, okay, like this many other packages, many more packages are available in R. Okay, so now we'll start with this. So basing on the request of yesterday's audience, one spectator requested to show the complete length code so that we can understand. So what I plan today is, okay, what I plan today is, first I will show you the meanings of every argument what we are going to use in every library. Then I will take you to the RStudio. Once I will stop screening, because as of now, with my knowledge in Zoom, one screen can be shared at a time. So I will just stop the screening and I'll open the screen with my RStudio. Okay, so first I will make you understand that what each argument refers to. Most of you might have been experienced and now have a little exposure that few of the arguments. Okay, but still there are some more new arguments that are to be observed and understand. Okay, yeah, we'll start with, we are going with iris data. Okay, this is where we are loading the data using the path where I have saved the data in CSV format. Okay, and library, I'm using the library. How to install a library? Install.packages within double quotation Scatterplot 3D quotation close, comma, dependencies is equal to true. True should be in capital letter. Close the parenthesis. Now this will enable you to install the package of Scatterplot 3D. I have already installed. Now I'm calling that particular package to work on with the functions available in that particular package. Okay. Now library Scatterplot 3D. Now the best usage of attach function is that to call the variables or objects which are available in the data set without any hindrances, or it can be a reference point that sepal length, okay, it belongs to SP, where the data is stored. Okay, a scatterplot 3D. 3D is nothing but we are having three-dimensional view. Okay, x-axis, y-axis, and z-axis. So the data points will be encapsulated in this form that this is x-axis, y-axis, and z-axis. The data points will be in this particular three-dimensional surface. Okay, so we are taking sepal length, petal length, and petal width. Okay, these are all the x, y, z, and then x-axis, y-axis, and z-axis. And PCH is nothing but pixel density, that how far I need to view the data point, showcase the data point in the graph. And color is steel blue. Blue, steel blue, red, brown, yellow, orange, anything you can use. Okay, now apart from that, here this iris data set has one categorical variable, that is what we call species. Species has three categories, right? Species has three categories. Okay, I will show you the difference. Let me explain this code, and again today I'll be stopping the screen and sharing the screen, or let me complete the entire explanation. Let us see. Okay, now the next code comes that we wish to display these three scatterness of the plot. Okay, scatterness of the plot use across the different types of species. How many species do we have in this data set? We have three. So the first one is colored with steel blue, the second one is colored with red, the third one is colored with black. That all being stored as a vector, and it is stored in a variable called colors. Now in this scatterplot 3D, The first three arguments stands for variable 1, variable 2, variable 3, and next the density of the pixel data point. Now another argument starts with color. Okay, in some other libraries it will be COL. Yesterday we have seen in histogram. Okay, in Boxplot that's just COL, but here in this Scatterplot 3D it is called color is equal to colors of. Since it is a factor variable, a categorical variable, we have to use one function called as dot factor. Treat this species as factor and apply colors to each species, starting with the steel blue, red, and black. Now you need grid equal to true. Grid equal to true means that is not a lower upper panel, and this in Excel you will get major grids and minor grids. Okay, in the similar fashion, grid equal to true. Here I have highlighted box is equal to false. Yesterday when we had yesterday also we have seen that outer layer of the graphical plot will get disabled. Okay, and now we are giving the labels. Okay, X label, Y label, and Z label. So these two, what is the difference? Now we will understand what is the difference between this code and what is the difference between this code. Okay, the first major difference is the first code is related in general to the 150 data points without any distinction of species. In general, we have taken 150 data points and let us see the distribution of the data points. But now, once we know and we want to make use of the data, that means one more variable which is available in the data set, that is species. Okay, now we want to color that particular species in across three particular colors for each color standing to one particular category of the species. Okay, and some other aesthetics what we have added is common aesthetics, that X label, Y label, and Z label. Okay, yes. Now we'll move further, that what is the another way? What is the another way to have a scatter plot 3D? Okay, in R, there is not one straightforward code available for 3D, three-dimensional view. There are different functions and objects available. Okay, functions available to depict the graph in a 3D view. Okay, here we use a function called width. Okay, with the data available in SP, project the scatter plot in. See here, scatterplot 3D as a, it works as a function separately. Within this function we are giving all these things, whereas when we use width, okay, when we use width, scatter plot will become one of the argument. All this code will become one of the argument. Just we are calling the data SP. That is the difference between this code and this code. So here with function, just additional argument what we have is the data set, and the rest of the thing is the same what we have seen here. What we have seen here. Okay. Now a little further. Okay, we'll do one thing. We'll just run these three lines and then these three things, and then we'll move to. Okay. Okay, I got it. I learned today how to do new share. Fine. Now, so this is what we are doing now. So what and all we have understood with the document, what we have seen now, we are trying to execute it. It requires little space in the plot so that for better view. Let me run line by line. First I'm loading the data. Okay, then I'm calling the library. Then I'm attaching the data to the R local library. Now, let me disable this. Okay, now we are depicting the scatter plot with a three-dimensional view. Whenever you place the cursor on the function of a particular library, it will show its general syntax. You can see X, Y, Z, color, PCH, main, sub, many things you can give. Okay, but we are using minimum arguments which are required according to the context. Now here, this is the what we call 3D view, 3D scatter plot. Okay. Now what I will add is, I will add box is equal to, sorry, small case, box is equal to FALSE comma. When I run this, if see, okay, so that layer, the box totally, which is showing as the cubical form, 3D cubical form, got disabled. Now, how to understand this? Here, we will be witnessing today in this morning time, the morning hour, we will be witnessing only 4 to 5 varieties of 3D data visualization, but my focus will be more on understanding each graph. Okay. Now see this, assume that we don't have the knowledge on the type of species. Observing this 3D graph, the sepal length and the petal width and petal length, I am able to witness two clusters, right? This is one cluster and this is another cluster. Okay, uh, understood? Right. Now observe one more thing. Except in sepal length, the petal length and petal width of one particular group was smaller, looks like smaller. It is spread across the x-axis, whereas the y-axis and z-axis are smaller. Okay. Now, when you see this, it is a one dense of plot, one cluster of plot. It is spread across all the three dimensions. Okay, fine, right? Um, so with this graph, what we have observed, it seems that there are two clusters. Okay, two different types of subpopulations are existing in this particular data. Now let us start doing the color appellates of per days. Now see, within this one particular, this is within this one particular thing, I have two different populations. I have two different populations with higher petal length and higher petal width, but minimum sepal length. Okay. Now here, why we have to have, this is where the concept of unsupervised learning will come. Okay. Okay. Means that if we don't know the class labels, then we assume, we believe from the graph that there are only two populations. But when we come to know that within this large density of a cluster of points, there are two subpopulations available with a commonality in some area of measurements. Okay. Now, what is the thing is, width function. Width function also gives the same. We can add X label, Y label, Z label also here. So both the graphs are one and the same. Okay, so either I can generate directly with sepal and sepal width, or I mean this Scatterplot 3D as a function, or I can generate with using width function. Okay, fine. Right. Now what I do is, now are you able to see the Word document now? Can anyone just tell me? Okay, I think side by side I should do. Fine. Now you are viewing the Word document. Okay. Now we go to another interesting part using RGL, rotatable graph libraries. Okay. With our own hand, we can easily rotate the graph. Okay. How to do is that there is a function called plot 3D. Again, three variables we have to give. The type P is nothing but points to be depicted. Okay. Size is 5. You can increase the size. Main is heading of iris data scatter. I can remove this. Iris data. Enough. Sorry. Iris data. Subtitle I can give rotatable 3D plot. Okay, here also I can give subtitle, but here also, here we are using one more argument called subtitle. Now Let me try to show you this. Yeah, fine. Let me complete one particular package and then we'll move to the other thing. Plot 3D, here we are adding additional things that the colors, already we have defined this color here. Already we have defined the color here. So no need to repeat again. Once it is called, we can do that. And thereafter we can see this adding of one more argument called color. The other argument box is false, and the title main is iris data, and subtitle is 3D plot. Now, what distinction, what differences you found between this particular line and this particular line is that we are representing the rotatable graph 3D library, 3D graph with aesthetics and removing the box. Okay, now let us do this. Arguments are very simple to understand. See, we are depicting 3D dimension, 3D view. 3D view means we need x-axis, we need y-axis, we need z-axis. Okay, how to present the data points? Type is P. What is the size? What is the size you want to depict? That is 5. I want the title of the graph main. So in every graphical presentation, you need to have labels of axes, main of the graph, and what is the pixel size, and what other and what variables are to be defined. These are all the common arguments that you have to remember. One is the variables that are to be depicted. Second one is the pixel density. The third one is the colors if you have want to have, and the fourth one is the labels of x, y, z axis if it is 3D, x, y axis if it is 2D, if it is x axis only one univariate dimension like histogram, box plot, you can give only x label or y label, and you can commonly you will have a main title for all the graphs. Sometimes if you want to restrict the limit of the axis, you can use another two arguments called x limit, y limit, z limit, but provided that library should have that argument or feasibility of that argument. Okay, not all libraries will have that kind of a limit restrictions. We have to check the syntax and make use of that particular limit of x-axis, y-axis, and anything else. Okay, now we'll do this. Okay, I'm calling rotated graph library. It is loading. It loaded. Okay, now I'm running the first one. When I repeat the first one, you can see there is a blinking option here. Let me share that now. I have a graph here. See this? Okay, now I can rotate. I can see, right? I can see from the top of the angle that, okay, this is one line of, I mean, the dispersion of the data points pertaining to one particular species or in one trajectory, the other one is another trajectory. So if you see this is sepal length, vertical axis is petal width, and again one more horizontal axis is petal length. So it is spread around the sepal length. Okay, now if you want to have the surface view, I can change this. See, let us take X, Y, Z. Now, data is in the surface area, right? Fine. Now, let me go with another way of depiction of colors. Another way is depiction of colors. Let me share the new screen now. What we have. This is the new screen. Okay, now I have made box is equal to false. Yeah, exactly. You can see this is x-axis, y-axis, and z-axis. Okay, now the data is on the surface. I can clearly see. This is the, I think this is one way to understand a 3D plot. That if you see this is what we call petal width, petal length, and sepal length. This is sepal length, petal width, and petal length. Okay. Now this group of dots, this cluster of dots are having a magnitude in terms of sepal length and not that of petal length, and I mean, no, in terms of petal length, not that of sepal length. Okay. Now, when you see this, clearly we can understand that this petal length is of this axis, petal width of this axis, sepal length is of this axis, right? Okay. Now, this is the 3D scatter plot of iris data connecting, making us very clear understanding that how the data points will be on the surface of the 3D plot. I can still rotate this and view. Now you can see one more view, that x-axis, y-axis, and z-axis, how the data points are scattered across the. You see, and one more point we see that there is a uniformity in the stretch of the data points. Lower petal length belong to one particular cluster, what do you say, species type. Higher values of the same petal length belong to another type of a species, but their magnitude is same. Okay, so we can save this exactly. Now the next question will come. The common images, the remaining images, what we have seen so far, we can, I have shown that click on the export button, we can save it as an image. Now the next question will come. If I have this kind of a video, I mean a moving, rotating graph, then how to save this? We can save. There is two options called movie 3D. Okay, movie 3D library or function, where you can use this, we can save this kind of a image as such. Whenever we open, then we can see that we will be able to have all the palettes that we can move accordingly and see whenever you want. Okay, now we'll move further with another lines, another lines called page. Okay, uh, pace. Okay, here what I did is, what I'm trying to do is, pace is one function, sp of 1 comma 4. First parenthesis I'm leaving blank because I want all 150 samples that are to be required for plotting the data, and I'm calling only 1 to 4. In the place of 1 to 4, if I want to remove, the fifth column, what should I do? In the place of 1 to 4, I can use -5, or I can use 1 to, if you know, if the data columns are minimum, then you can restrict to 1 to 4. Okay, and PCH is 19. And there is one more argument in the lower, but the remaining things are same, but additional argument is lower dot panel is equal to null. Means generally when we create, what is the main what is the main function of this space is, it will create a matrix scatter plot. How many variables are there? 4 variables are there. It will create 4 cross 4 matrix scatter plot. Okay, the lower panel is a replica of upper. The lower panel is a replica of upper. So since it is a matrix form, square matrix form, we can disable the lower panel and we can have only the upper panel. So for which we have an argument called lower dot panel is equal to null. If you want upper panel to be null, you can use upper dot panel is equal to null. Okay, we'll do this and then we'll move to another graphical point slowly, right? This is what I said. Okay, this is what we call matrix scatter plot. This is what we call matrix scatter plot. That what is the relation between, what is the main purpose of scatter plot? To see the intensity of data points between two continuous variables. Okay, now how to understand this? Let us generate the next code so that we can have the clumsiness, overcome the clumsiness. Okay, now this is so fantastic, so easy to understand. Okay, now what sort of observations we can make out of this particular graph? Okay, what is the relation between petal length and petal width? But there, in every graph you are observing two clusters, right? Okay, now how to understand this? This particular, in with this particular cluster, The petal, as increasing the petal width, there is a increasing in the petal length as well, in a magnitude of positive direction, and has a good intensity density of points clustered around, very close by. Very good amount of neighborhood points are available within this particular cluster. Now what about this? This also has an increasing, but within the short axis, this particular cluster has a small length of petal length and petal width. Both the clusters are depicting the same trajectory, but this particular type of a subpopulation possesses smaller measurements of petal length and petal width. But there is another cluster where the petal length and petal width is little, I mean, at most higher, better, I mean, at the higher levels than this cluster. This is one observation. Now, coming to this is the scatter plot between sepal length and petal width. Sepal width and petal width. When you see this relation between sepal width and petal width, what you are understanding, one particular one particular cluster, that within the small range of petal width, its sepal width is varying. See, there is a trajectory in a vertical side, means that particular species petal width has a minimum range of its height, okay, measurement, okay, minimum range of its measurement. Okay, I repeat again, there is some thing here. I repeat this. Petal width has a small range. How to understand the range? You have the axis measurement here. Let us take from 0.0 to 0.8. Within the range of this petal width, the sepal width is varying from 2.24. So what does it sense? What does it make a sense here? That this particular species, petal width will be smaller, but petal sepal width will be larger. So this particular species will possess a longer sepal width measurement rather than a smaller petal width. Similarly, if you observe sepal length and petal length, so these two are having the same characteristic. Okay. Now coming to sepal width and petal length, same. Sepal length and petal length. So more or less, this cluster of points, okay, is having larger width with respect to sepal width, sepal length, and and petal length. But the petal length and petal width are smaller. So one particular group of species is having a wider range of measurements in terms of sepal width and sepal length, not that of petal length and petal width. Okay. But whereas coming to other cluster, now see this box, that is 1, 2, 3. This is one, and this box. They have this almost same trajectory with this density. Means they have they have a wide range of petal width, they have a wide range of sepal length, but they have they have wide range of sepal length, petal length, as well as petal length, but the density of this particular scatter plot is not ranging towards the maximum range. It has some restriction less than 4. So this particular cluster of species is having the lesser measurement, the wide range of sepal width is minimum with respect to that particular cluster, whereas sepal length, petal length, and petal width are at the wide range of, they have the wide range. So two major points that are to be noted is, there are two clusters. One cluster has a behavior with the smaller values of petal length and petal width, whereas the same small cluster has a wider range of sepal length and a moderate range of sepal width, a wider range of sepal width and moderate range of sepal length. Now coming to the large cluster, okay, what it is exhibiting is that it has the wider range with respect to sepal length, and petal width, and a moderate range of values with sepal width. So this gives a clear distinction that One is counterpart of the other. Okay. Now we will make use of some more interesting features. Okay, some more interesting features with this, for which I'll show you some other graphs. Yeah, this is quite interesting. I think you will love by seeing the graphs what we see here. Okay, now see, here I'm using two libraries, G Gallery, Graphic Grammar Gallery, or Graphic Gallery we can say, ggplot, Grammar of Graphics. Now, first I want to use, I want to depict the same plot, okay, same plot without the category variable, that is species column. Now, with the species and coloring them. Okay, I have only two arguments here. Okay, SP is the data, aesthetic stands for color. Okay, now next thing is this species has three types of species, that is versicolor, setosa, and virginica. But I can restrict the required number of rows, that is 1 to 100 stands for first two species. Okay. Similarly, I can do with another 51. I have to take my choice of 51 to 150. One may raise a question that I want to select the first species and third species. How to do? Then you have to use C of 1 to 50, comma 1 to 50, comma 51, 101 to 150. So that particular range between the parentheses will call the first species and third species. Okay. Okay. The commonality what we observed is data calling is must. If you want to add color, you have to add aesthetics. Okay. Now let us do this one by one. Let us do this one by one. Okay, now I'm calling G Gallery loading package. Yes, it got loaded. ggplot already we have called, I think so. No, not yet. Okay. ggplot we have done. Now the ggpaste will give me, it is executing. This is what is we say. This is the ggpaste. Okay. Clearly notice, let me zoom it in a thing. Let me zoom it to a thing. Share the screen now. Now see, we maximize it to full screen here. You can see the heading sepal length, sepal width, petal length, and petal width. And here also it's a square plot. Fine. It has three different statistical depiction. Number one, scatter plot across each matrix of scatter plot across each pair of variables that we have seen as a separate using pair function. Number two, the density plots. The density plots in each pertaining to each variable. Okay, this is without species, assuming that I don't know the subpopulation in the data. I'm just plotting the data of 150 samples and I'm just viewing what it is ready to tell us to understand. Okay, and the third measure is the correlation. Correlation between sepal width and sepal length, correlation between petal width and sepal length, correlation between petal length and sepal width. This is how you see in the correlation matrix, the same way you have to understand. Fine. Now, how to make observations out of this such kind of a graph. Now, you see, there is a density. One in first look, we observe there is one density here. There is also one density plot here. But here, coming to the petal length and petal width, it is a kind of a bimodal structure. You can see a bimodal structure. Means, with respect to petal length and petal width, the clear distinction which is being depicted here, that which is depicted, and the same is not being done by sepal width and petal, sepal width and sepal length. So what we need to understand is that petal length and petal width might be a most supportive variables to identify the subpopulations within this 150 samples rather than sepal width and sepal length. But now we have to make one more keen observations with a magnifying thing, that observe, does does histogram, does the density plot of the sepal length is as such of this sepal width? No. Observe, there is a slight peak and there is a dip. Again there is slight peak, again there is a dip in the curve. That means to some extent there is a overlapping here which is hidden, and the sepal length is not trying to exhibit as petal length and petal width is doing, but it is trying to exhibit that even sepal width is also trying to exhibit that there are two subpopulations, but the measurements of those populations are overlapping or common in nature with respect to sepal length and petal width. But those measurements are little farther or little distinct with respect to petal length and petal width. Fine. If you are not satisfied with this, we will make use of, assuming that we have identified the clusters, we will try to do some other thing. Okay. Now the same thing will be depicted, okay, using the categorical information of subspecies type. Okay, it is executing, it is depicting the thing. Yeah. Okay, let me share this as a new window. Now, here, when compared to the previous graph, it has lot more statistical summary measures and graphical measures, graphical tools. What and all we have? How many tools we have? How many tools we have? One, it is a bar plot. It is a bar plot. Okay, it is a bar plot of Setosa, versicolor, and virginica, and then box plot for each variable across the three types of species. Okay, then histogram, histogram of each variable, histogram of each variable according to the color. Number 1, 2, 3. Number 4, scatter plot with respect to color distinction of each species pertaining to the pair of variables. This matrix plot is sepal width and this is petal width. Okay, number 4 is over. Number 5, this is called density plots. Okay, this is called density plots between the petal length and with respect to petal length. This is with respect to sepal width. This is with respect to sepal length. Okay, number 5 is over. Coming to the number 6, correlation on the total, correlation between petal length and this is the correlation of setosa pertaining to each category type, each subspecies type. The correlation between sepal length and petal length is 0.267. But sepal length and petal length in versicolor is 0.862. Okay. Now this is one snapshot of 6 statistical measures and graphs that which will enable us to write a lot of information and we can understand very easily. Now, first thing what we have to do is, in the previous graph, we have seen a small mode here, and again there was a density coming down. Okay, that peak and the remaining were not able to distinguish because the blue is nothing but virginica and versicolor. With respect to sepal length, they have almost common measurements. Sepal length measurement is almost common because it is a overlapping densities. At most overlapping is observed with respect to sepal length between versicolor and virginica. That's why the earlier picture wasn't unable to show that trimodal structure. But whereas there is a peakedness in the data pertaining to the Setosa species, that sepal length is having a higher measurement in subs of centimeters than the virginica and versicolor. That's why this peak has shown that a small tip in the previous graph. Now, you might have witnessed that in sepal width, there was a single density because this, with respect to this sepal width, all the three subpopulations are having uniform measurements. Okay, that's why it wasn't unable to depict the clear distinction that it possesses three populations within it. Now, coming to petal length and petal width, there was a bimodal structure, right? Hope you recollect. There was a bimodal structure clearly in the previous graph. Now, why bimodal? Because the measure, if you see the measurements here, take the measurement horizontal line here, the measurements pertaining to petal length and petal width pertaining to Setosa are quite in higher, larger quantity than the other two species. Okay, because of the commonality with respect to the peak of these densities, it came out as a only one model. This is one mode and other curve, other mode. Okay, so there is a overlapping between versicolor and virginica with respect to petal length and petal width. But whereas this setosa is clearly distinct in terms of three parameters, that is sepal length, petal width, and petal length. Okay, but when we take this as a classification problem, then what we can understand here is a classifier rule, a multi-class classifier rule which we generate can clearly allocate the species of Setosa, because in three different parameters, it is providing a distinct phenomena, behavior, rather than the virginica and versicolor. Okay, we need some good algorithm, good kind of a programming or good kind of a statistical method, advanced method, to have a better distinction that how best we can classify or how best we can allocate. If I found a new iris plant, okay, if I start measuring the petal length, petal width, sepal length, and sepal width, how best I will be able to allocate that, identify that this particular species belongs to versicolor or virginica. Okay, suppose if the petal length is larger, around 5.8 centimeters, if the petal width is larger to 2.4, if the sepal length is larger to 1.2, then clearly distinguishes that that particular iris plant belongs to setosa. A slighter clumsiness observes with virginica and versicolor. But when we build this model, logistic regression or any other ROC curves, the percentage of correct classification between petal length and these three is 100%, but it comes around 98.4 or 99.2. At most, correct classification can be done. That remaining 0.8 or 0.1, 0.2, and 1.2 is a error classification. Okay, error classification. So, and yeah, and this is the correlation values. Now, in yesterday's class, the same box plots we have depicted as a separate graph, but in this, it has become one part. When you use this code for the data set what you have to project, especially supervised learning techniques, okay, this will give a complete phenomena or a kind of a scenario of the data set, that how the median levels of three different categories are varying, how the density plots are varying. Okay, what is the correlation between these three variables across in each type of subspaces, how the density plots are scattered across the xy plane corresponding to each pair of values, how the histograms are overlapping with respect to the data what we have corresponding to each variable across three species, and what is the discrete variable, that is count data information pertaining to the categorical information. So this much we can write, that data is ready to tell something, we need to listen to the data. Okay, just with a grasp, with a blend of statistical knowledge what we have, we will be able to what do you say, we'll be able to connect to that particular information what graph is depicting. I always prefer and I always request every one of you to start the analysis with graphs. Then you will understand that how many patterns are hidden in the data and what kind of a behavior in XY scatter plot it is witnessing. And can we, if I fit a straight line, will that fit properly? Okay. Yesterday there was a request to have a polynomial regression. I will have a second order polynomial regression. I have a data set that I will show you if I fit a straight line of that particular curvilinear approach, to what extent my model will be fit. Suppose if I have a second order polynomial, to what extent the curvilinear approach will fit to that model, and can I compare the straight line, which is the best one, that is a straight line or a second order polynomial, I can do. There are some methods. I will explain that when we deal with the regression concept. Okay. Now, we'll move a little further. We'll move a little further. We have some more things to see. Yeah, density plots. What we have seen earlier, that they in a diagonal line, that density plots. Suppose if you want that particular density plot separately, okay, it depends, right? I want to only present the density plots, not the total snapshot of a cheat sheet of 6 varieties of statistics. I want only density plot. I want only box plots to be depicted. Then what I do is we use a function called qplot. Qplot is nothing but it can be done variable by variable. Okay, it is a univariate, but it can be overlay. We can project the overlapping histograms. It can project the overlapping histograms. So sepal length is the variable that I'm interested to do. Data I'm calling, that is stored in SP. Geometric is the density I want. Fill with species. Fill with species. Alpha is indexing that 0.5. Main, title, X label, and Y label. Now, coming to the next code is nothing but creating the, what do we say, this, what we say, a square kind of a box which is divided into 2 rows and 2 columns. Okay, 2 rows are this is categorized according to the categorical variable. I mean, divided according to the categorical variable. I'm using LBW data because this iris data has only 4 continuous and 1 categorical. I want to make use of some more categorical variables. That's why I'm recollecting this LBW data. I'm using on x-axis mother's weight, on y-axis baby's weight, and data is loaded in LBD. That is what we have seen here. And the geometric presentation of the data should be with Boxplot and jitters. Jitters are nothing but the data points that are to be thrown on the Boxplot to see the scatterness of the data points across the range of the Boxplot. Now fill across to race. Race means we have white, black, and others. So construct the Boxplot and using the jitter for the variables LWT and BWT across the each category of the race, main data, and X label and Y label. The next thing will come is that, sorry, this will give one panel. I mistakenly said that this will give one panel. This facet is nothing but we have 2 levels of smoke and 2 levels of hypertension. So the entire plot will be divided into 2 cross 2 contingency kind of a table. Within that, the values of low birth weight and mother's weight and baby's weight will be depicted, and with coloring the normal weight of the baby and normal baby low underweight of the baby. So let us try to do this. Oh, I have to share this now. Okay, I have loaded this. Let me generate the first density plot of that. Yeah, see, If I want only one particular, if I want only the sepal length, then I mean density plot of one particular variable, then I can do similarly. Now, yesterday what we have done, we have four variables. I want to have four things. Just what you do, we have to use par, sorry, par mf row split the total plot into 2 cross 2 and then repeat this code 4 times. Just change the variable name. You will get four curves, one, two, three, four, four images of density plots with respect to sepal length, sepal width, petal length, and petal width. Okay, can we do that? Okay, for just time being, I mean, for understanding, making you understand that I'm doing this. It is very easy. Okay, let me generate the 2 cross 2. I'm not changing any other thing, just I'm changing the variable. Okay. I think par MFRO will not work for this. Okay, so like this you can have image of each density plots. Now we'll move further. Let me try one more time after some time. Okay, it should work actually. Why it is not working? Okay, let me check that. Now we'll go with another presentation. I'm loading the cube plot. This is what I said. Okay, this is what I said, that I'm creating the box plot for each race type, black, other, white. Okay, and the jitters, the argument jitter is to throw the data points pertaining to the white population, other population, and black population across this box plot. Now, if you see, there are some, the wide range of this box plot is different from each race. The range of this horizontal is different from the range of this horizontal, and this also little horizontal distance is different. So the horizontalness will tell us the leptokurtic, platykurtic, and mesokurtic. Okay, and the position of this particular box plot will tell us it is symmetrically distributed or right skewed or left skewed. Okay, now apart from that, this jitter and box plot together will tell us two more interesting measures, that is what we call outliers and extreme values. What is the difference between outlier and extreme values? Okay, extreme values belong to the same trajectory, but they are having huge gap within the density of the points. But whereas are, outliers are the, let me correct, outliers are the values which are in the same trajectory, but they are at the farthest point and has some gap between the one density and that particular point. Whereas extreme values, they do not belong to that particular density of point, but they are one point which is above that particular range of this horizontal distance. We can witness both same here. This is an outlier. It is in the same trajectory of the data points, but it has the distance. Okay, it is, it has a huge gap between the cluster of points, but it is little farther. You can see here, this is an outlier. Now see these observations. These are all called extreme values. These are all called extreme values. Neither they are within the range of the thing, neither they are within the vertical axis, they are little away. That means they are not to the density of data points, they are little away from that. They are called the outliers. Okay, now we have one more graph to go to understand. Yeah, so this is what I have used facets. Facets is the argument to split the panel into 2 cross 2. Not necessarily 2 cross 2, whatever the dimension. If I use race, it will create 3 cross 2 because race has 3. Okay, what it is trying to tell us is Mothers with normal weight, baby's weight is the color distinction. Pink color shows that low birth weight babies, and blue color, pale blue color shows the normal weight babies. Okay, now no hypertension, non-smoker. There are majority of the data points where the baby belong to normal weight. Mothers who have smokers, who are smoker and no hypertension, this is the data points where babies are of low birth weight. So no hypertension, even in this no hypertension segment also, there are good number of points prevailing, observed to be belong to normal weight, meaning that hypertension might be a very important parameter where mothers has to take care of, so that baby's weight, or it should not influence the outcome of the baby's weight. Okay, and there are limited samples with respect to hypertension and smoker. Okay, of the 5 samples, 3 samples are loaded with low birth weight. So if we have more balanced samples with respect to hypertension and smoking, then we can make a understanding that mothers who have hypertension problem as well as smoking habit, then the samples and the babies may get affected with low birth weight. So this sort of observations we can make. All what we have discussed now is called exploratory data analysis with graphs and summary statistics. Okay, now what I do is, because I can show you lot many things, but at one stretch, if I show lot many things, what will happen is it will be an overlaying thing, and we can practice. We can start with some functions which are known to us. We are exposed to them. Then slowly we can start practicing thereafter with additional arguments and features. Okay. Okay, fine, fine. Because we started late. Okay, that's why we started around, due to some technical issue, we started around 11:40, 10:40. Okay. Okay, do you have any questions? Thank you. Didn't get the concept-based webinars in future must be organized. Thank you so much. Okay, fine. Do you have any questions to ask or what? Okay, okay, wait. Can you place the difference between outlier and extreme value? Outlier is nothing but within the same trajectory of the scatter. Let us take a scatter plot between sepal length and sepal width. Okay. You have a trajectory of data points that increasing length of sepal length, and there will be increasing level of sepal width. But there are 1 or 2 points. Okay. There are 1 or 2 points which are little farther in the same trajectory. Those things are called outliers. Okay, when we find some gaps between the data points, 1 or 2 points they have little farther from the same trajectory of the cluster, then that point is called outlier. Now, we have an ellipsoid here. I mean, let us take the outer line of all those density. One point is above the that particular contour. Then that point, which is not according to the trajectory, but it is on the above the ellipsoid, is called extreme value. How to save? 1 minute, I have missed one question. See, two variables, how can we draw 3D graph? Okay, it's a three-dimensional view. Okay, to have a three-dimensional view, we have to use. We can give directly, but it is better to define it and then define it as a factor. Okay, to just reduce the clumsiness and functioning in a proper way. Okay, to save the 3D graph, especially RGL, I will club two questions here. To save the particular RGL, there is a function called movie 3D or scan 3D. Using these three, scan 3D or movie 3D, we can save as such. Okay. See, Boxplot is a very basic summary plot which is a 5-point summary graphical technique tool, which will tell us the first quartile, second quartile, I mean Q1, Q2, Q3, lower interval and upper interval. Okay. The main purpose of Boxplot is to observe the normality. Okay, observe the normality in terms of the stretch. If the whiskers, I mean, if the median is positioned at the center, it is a one indication that the data is normally distributed. Okay, and second thing is if the horizontal axis of the box is little wider and wider, it shows that the data is becoming platycartic. I'm clubbing the questions now. Okay, now if the data is horizontal axis is widen and widen, it shows that widen and closer and closer is that it is a leptokurtic. Okay, it is a leptokurtic kind of a thing. So the horizontal version and vertical of that particular box plot will tell us whether the data is platykurtic, leptokurtic, that is kurtosis, and skewness is positioned based on can be understood based on the uh, position of the median, right? Fine. Fine. Hope I have cleared all the doubts. Arguments requires little patience. Okay, fine. Anyway, so we'll meet you again around 3 o'clock. Even from my side, there was some technical issue to log in this morning. Okay, so that's why I couldn't make it by 10:30 sharp, but I'll be ready by 2:45, 2:50 now in the afternoon. Tomorrow, this afternoon, we'll be understanding the essentials of hypothesis testing, and we'll cover some basic statistical tests that are available in understand how to handle the hypothesis framework of a statistical data. Okay, so with this we'll conclude now, and then this afternoon by 2, I will be joining by 2:50 or 2:55, and you also be ready by the same time. Thank you.